So in this lecture, we want to start to understand nuclear physics, or in other words, the physics that goes on in the nucleus of an atom. For beginners, let's start to understand how we discovered the nucleus. In the late 19th century, James J. Thomson discovered the electron, and he knew the electron was a component of atoms and that it was very light with a very large charged mass density. So they knew that it couldn't have the majority of the mass of an electron. So they developed a model, sometimes known as the plum pudding model, which just said that the atom was a whole bunch of positive stuff. And that within that positive stuff, like raisins or plums in a plum pudding, they had lots of different electrons in some kind of a pattern, and those electrons could vibrate in their various different positions, and that would set up the different kinds of electric waves that came off of atoms. Now, a man named Rutherford wanted to explore this idea. And so what he did was he figured he couldn't get any light that was small enough to look at an individual atom. But if he found a hard enough particle, he could blast it through there. Now, certain kinds of materials had been discovered to emit rays known as alpha particles. Now, we now know that these alpha particles are simply helium-4 nuclei. The same kind of helium you use in a balloon. But he had this alpha source that shot this heavy charged particle at a thin gold foil. Now, if the gold foil had in fact been a mushy goo the size of an atom that was all evenly distributed positive material, then that alpha particle should have gone right through it, essentially unimpeded. It would get knocked around a little bit by interacting with the electrons, but the positive stuff was so spread out, it would never have any interaction. So that's what he was expecting to see. He used this lead-lined source to collimate or make the alpha particles come out in a single straight line. He shot it at the gold foil, and then he had a detector here, and he would count how many of the alpha particles that came out were deflected or turned to an angle phi. He expected essentially none would be turned more than just 1 or 2 degrees, if that, away from going straight through. This is what his actual data showed. Most of them did in fact go straight through. However, a surprisingly large number turned through angles much larger than he ever would have expected in the plum pudding model. Notice here at an angle of 60 degrees, it's still only about 100 compared to nearly 10 million that come through at a smaller angle, at nearly 0 degrees. But that's still a much larger angle than he ever thought possible. He once remarked that this was, to him, like firing a cannonball at a piece of tissue paper and having the cannonball bounce back. This mushy idea of all the mass spread evenly throughout the atom would be like that tissue paper, and the alpha particle like the cannonball that should have just shot right through it. And instead, it bounced back at a large angle. In fact, significant numbers bounced back almost straight backwards. The only explanation he could come up with for this, and the explanation we now consider to be correct, was that instead of all the mass being evenly distributed throughout the atom, most of the mass and all of the positive charge had to be concentrated down in a very small region, with the electrons orbiting around the outside. Now, I've drawn this nucleus to be small, but it's not nearly small enough. The nucleus is 5 orders of magnitude smaller than the electron orbitals, or in other words, 100,000 times smaller. I like to imagine if the nucleus were a grape at the 50-yard line in a football stadium, the electron cloud would be the size of the entire stadium. So the mass is all concentrated in that little tiny dense nucleus. That way, when the alpha particle comes in, most of the time it goes through totally open air and is totally undeflected, just as was predicted in the plum pudding model. But if it happens to come close to the nucleus, then it can get much closer with much more of that charge concentrated inside, closer in than the alpha particle, and we can get a very large repulsion. Remember, Coulomb's law is that the force is kqq over r squared. If the charges can be closer together, then we can get a much larger force, enough force and enough momentum to actually turn this through a large angle. And that is how they found out that most of the mass of an atom is concentrated near the center, and they named that concentration of mass the nucleus.